one example of existence and uniqueness in terms of arbitrary initial condition, essentially, that is y of x naught is y naught. After that, we discuss one method of variation of parameter for to solving first order linear differential equation. So first we solved it the homogeneous part, and then we solve the general equation, which is a non-homogeneous equation, and this is the formula of the solution in of the first order linear differential equation. And then we have seen one example. So what we started in the previous lecture, new thing is second order differential equation, and the first example which we have considered is a linear differential equation, which is the general form of the linear differential equation is of the form px y double dash plus qx y dash plus rxy is equals to c times c of x, where these functions px, qx, rx, and cx are continuous functions over this given interval I. Right. So this is general form of second order linear differential equation, and we'll call it homogeneous whenever this part is zero. The right hand side part, whenever we write down the differential equation in this form, and right hand side the cx function is identically zero at every point, it is zero, then such a differential equation is called second order homogeneous linear differential equation. Otherwise it is called non-homogeneous. And if y1 and y2 are solution of the homogeneous differential equation, then y1 plus y2 is also solution of this equation. That is easy to check, and any number times y1 is also solution. So that means the solutions, the set of all solution makes a vector space, right? So clearly this solution space contains the zero vector. What is zero vector here? The zero vector is the continuous function, because all solutions of these differential equations are the functions which are not only continuous, they are differentiable 2 times. Right. So 0 is a trivial solution whenever the differential equation is homogeneous. So that case is similar to the homogeneous linear system of equation. There also we have zero vector is a solution. Here also we have a zero vector is a solution, but here zero vector means it is a continuous function which is identically zero. That is zero vector. The same way for the set of continuous functions, we can define linear dependence and linear independence. So the definition we have discussed in the previous lecture. And Wronskian, we define certain terminology. If two real valued continuous functions on an interval are given, then how to check whether it is linearly independent or dependent? So that depends on the Wronskian. So first of all, this definition of Wronskian, and we check that the Wronskian of the function cos x and sin x over any interval, it is 1 for any value x, right? So the Wronskian, which we have defined at a particular x, but for every x, cos square x plus sin square x is 1, so that means Wronskian is non-zero in this case. Yeah, so the connection of Wronskian with linearly independence and dependence we will discuss in today's lecture. So first of all, let us write down the initial value problem, the existence and uniqueness theorem in the case of second order linear differential equation. Yeah, so every linear second order linear differential equation has this particular form, but this form we can always, whenever px is non-zero, we can divide this equation by px, right? Px is the coefficient of y double dash. So whenever this px function is a non-zero function everywhere over this interval I, we can divide this interval, this equation by px, and we can make the coefficient of y double dash to be 1. Right, so let us start with that. So consider the second order. Second order linear differential equation. The general form we can write by making coefficient of y double dash 1 will be of this form. So if you confuse with the earlier p and this p, then we can also use, instead of px qx, we can use ax and bx here. Right. So essentially this p is different from this p. That is what I want to say. Yeah. So where what is I? I is the interval which is in on the x-axis. Yeah. So but what is the corresponding? Yeah. So when we say this differential equation is homogeneous, so whenever the Rx part is 0, right? So let us discuss the existence and uniqueness theorem here. So for the first order differential equation in the existence and uniqueness theorem, we have taken one initial condition. This is a second order differential equation, and that is the why it is obvious that we will take here more than one initial condition, particularly two initial condition. So let us consider the given differential equation. Equation 1 along with initial condition so first condition is y of x naught is equals to y naught, or we can say this is some fixed number. Let us say it is k, right? And second initial condition we will take in terms of the derivative of the solution y. So that we'll call it some number. Let us say it is either k1 k2 or whatever c1 c2 we can say. So this initial value problem is given, which is this differential equation along with these two conditions. Y of x naught is some number, y dash of x naught is some another fixed number. So in this case, what we get is then this initial value problem has a unique solution. Right. So solution exists in this case, and the solution is also unique. So if you recall from the previous lecture, recall that here we assume that these coefficient functions px, qx, and rx are continuous functions. Continuous functions. Yeah. So this is regarding existence and uniqueness theorem for the non-homogeneous case. So for the first order linear differential equation, we have assumed a condition in terms of partial derivative for the uniqueness part. But here that condition is not required for the second order case. Only thing required is that these functions are continuous, px, qx, and rx. So where they are continuous, basically on the interval I. So as a corollary, we get special corollary, we get the homogeneous case. So that means whenever we consider the differential equation, which is y double dash plus pxy dash plus qxy is equals to 0, right? And here x belongs to I, and px and qx are continuous functions. Along with the condition, so since it is a homogeneous equation, the condition will take is y of x naught is 0 and y dash of x naught is also 0, right? So this essentially this k1 k2 we are selecting here to be 0. So then from the above theorem we get a unique solution, right? And that unique solution satisfies these initial conditions that y of x naught is 0 and y dash of x naught is 0, right? But on the other hand, we also know that every homogeneous equation has a trivial solution, that is y is equals to 0 everywhere, identically 0 function. So that means here we are not getting the information that the solution is unique. Since the equation is homogeneous, we know that the solution will be y is equals to identically 0 function, right? So this thing we are going to use in certain computation in terms of Wronskian, so that we can identify the given function, whether it is the given solutions, whether it is linearly independent solution or it is independent solution. Okay, so let us consider this result. So let y1, so we call this homogeneous system to be equation number 2, right? So let y1 and y2 be two solutions of the second order linear homogeneous differential equation. So we are not considering here initial value problem. First, we are considering only differential equation. So the differential equation we are considering is y double dash plus px y dash plus qxy is equals to 0. Right. So we have two solutions of this homogeneous differential equation over the interval I. Then for each point in the interval, we will get a certain formula of the Wronskian. So this formula is Wronskian defined at x naught. So basically this is we are evaluating at the point x times e power minus of x naught to x qs ds. Right, so this is in the power, exponential power. And once we derive this formula, we can easily check that the Wronskian, which is a function of x, is non-zero at a particular value x naught if and only if it is a non-zero for every x in the interval. Right. So this will help us to check the whether given solutions are yeah. So for solutions y1 and y2, this result will help us whether the Wronskian is non-zero at every point, or using this result we can check the same condition for only single point. Right. So application we'll discuss later on, but let us first try to prove this simple result.
So,
Yes.
so what is this S integration QSDS?
That is just a variable. You can take t or whatever. So basically, that variable should be different from x, because we are taking integral from fixed number x naught to x. Right.
Okay.
So q is this function, basically coefficient of y. Okay. So the proof. Let us start the proof. So first of all, let us recall the formula of the Wronskian. So for each x point in the interval, we have already defined the Wronskian to be y1 y2 dash minus y1 dash y2. Right. So that is this determinant which we have considered in the previous lecture. This one. So this is our Wronskian, and yeah. So every time we will, I may forget to write y1 of x. Right. So simply we'll write quickly y1 y1 dash minus y1 dash y2, and we'll keep in mind that this y1 y2 and y1 dash y2 dash are functions. Right. So now what is the, let us differentiate this formula. So if we differentiate this formula, we get derivative of the Wronskian to be the derivative of the right hand side, and if we differentiate right hand side, we will get y1 dash y2 dash plus y2 double dash y1 minus y1 double dash y2 minus y1 dash y2 dash. Right. We have differentiated both the sides with respect to x, and then we can cancel out the same terms. So y1 dash y2 dash, we have two terms plus and minus sign. So essentially this will these two terms will cancel out, and what we'll get is y2 double dash y1 minus y1 double dash y2. All right. Now we already know that our y1 and y2 are solutions of this differential equation. So that means y1 double dash plus px y1 dash plus qx y1 is equals to 0. Right? Just substituting y1 in the equation instead of y. So that will give us, yeah, so what we get is y1 double dash plus qx y1 dash plus rx y1 is 0. Right? Because y1 is solution of the differential equation. So from this we will get y1 dash. Similarly, we get y2 is also solution of the given differential equation. So these two facts we are using in this step, in the next step, that is, we'll just substitute from this y2 double dash, so that will give us y2 double dash to be minus qx y2 dash minus rx y2, right, times y1 minus, we can substitute y1 double dash from the first equation, so that is y2 times y1 double dash is minus qx y1 dash minus rx y1. Right, so just substituting y1 double dash and y2 double dash, we'll get this equation, and then we can cancel out the common terms. So rx terms in the first part is rx times minus y1 y2, and here we'll get rx times plus y1 y2. So that rx term will cancel out. What will remain will be the coefficient of qx, and that we can easily check that it is y1 dash y2 minus y1 y2 dash, right? So now this term is a bit known term, so that is essentially in terms of Wronskian. Wronskian is y1 y2 dash minus y1 dash y2, right? And here what we got is y1 dash y2 minus y1 y2 dash. So this is essentially negative of the Wronskian, right? So what we got is derivative of the Wronskian is minus qx times Wronskian. So let us write down this. Therefore, d by dx of the function of x is equals to minus qx times Wronskian. So we can take this on the other side. We get this one. So that means the Wronskian is the solution of this first order homogeneous linear differential equation. And then from the the variation of parameter method, we know what is the solution of this equation, that we can rewrite using this formula, right? So this part is 0, so essentially we'll get constant times this one. So that is solution of the homogeneous equation. So Wronskian, which is a solution of this first order linear differential equation, that is constant times e power minus qs ds, right? And then we know that the constant c, whatever we will get here, this one, that we can evaluate, and that is essentially the Wronskian defined at x0, right? So that is coming up because of the substituting x0 in this equation, right? So whenever we substitute x0, this part will be e power 0, that is 1, right? So therefore we will get the solution. Yeah. So what essentially we got is, we started with the Wronskian, we differentiated Wronskian, we have verified that Wronskian is the solution of this first order linear differential equation, and then solution of the first order linear differential equation, we evaluated Wronskian at each point x. So now in this formula, if we substitute x to be we can see that if this coefficient is 0, then the Wronskian is 0 at every point x, right? So we can rewrite this: if Wronskian is 0 at some particular point, then Wronskian is 0 at all point in the interval, right, from this previous equation. And converse is trivial, because if Wronskian is 0 at every point, it is obviously 0 at some particular point. So therefore, instead of checking Wronskian is 0 at a particular point, at every point, we need to check that Wronskian is 0 at a particular point. That is enough. Okay, so let us see one application of this theorem. So that will give us whether the two solutions are independent or they are dependent. So if y1 and y2 be two solutions of the so what is this? So let me write down the differential equation. Differential equation is y double dash plus qxy dash plus rxy is 0. So homogeneous equation we are considering, homogeneous linear equation. So how to check whether these two equations are two solutions are independent or not? So then y1 and y2 are two linearly independent solutions. So we'll check this using the equivalent condition, that is the Wronskian, that is in terms of Wronskian. So if Wronskian is non-zero, the solutions are independent. So okay, so let us try to prove this result using the previous method. Yeah. So in this case, what we need to prove, let us start with the condition Wronskian, the converse part. So suppose Wronskian is non-zero at a particular point, right? And consider two equations. So if we have two equations, which is linear differential equations. So consider two linear equations, c1 y1 x naught plus c2 y2 x naught is equals to 0, and the second equation is c1 y1 dash x naught plus c2 y2 dash x naught is equals to 0. Yeah, so for general x, basically we are considering. Yeah. So if we substitute in these equations x naught, then we get these conditions. So the question is to identify what we want to check. We want to check the given equation is these functions are linearly independent or not. So to check these functions are linearly independent or not, we need to take the linear combination of these equations. Right. So I have not mentioned that step earlier. So suppose this is given and c1 y1x plus c2 y2x is equals to 0. So this is linear combination of y1 and y2. And this linear combination which is given, from that we get the linear equations, these two linear equations. So how do we get this equation? First equation is same as this equation, but second equation is derivative of this equation. Right. So as we have mentioned, first I am taking arbitrary x, but later on we are going to fix this x naught using this condition that Wronskian is non-zero. So what is our goal? We assume that the linear combination is 0. The goal is to show that C1 and C2 is 0. Right. So this equation, if we substitute x naught in this equation, we get this corresponding equation. So when we substitute x naught, now these terms are fixed. So what is changing is C1 and C2. Right. So let us consider this equation number A. So what we know is Wronskian is not 0. So since Wronskian, which is y1 x naught, y2 dash x naught minus y2 x naught, y1 dash x naught is non-zero, the system of linear equation which is A has unique solution because it is a homogeneous system of linear equation in variable C1 and C2. So that is solution which is unique, and that solution is C1 is equals to 0 and C2 is equals to 0. So by assuming that we are given a linear combination of y1 and y2 which is 0, we proved that C1 and C2 is 0. That means y1 and y2 is our independent solution of the given differential equation. Independent solutions of given equation. So one part we have proved that whenever Wronskian is non-zero at particular point, that is only thing we need to conclude the solution is Li. Now converse of these. So in converse, what we need to show? We need to show the solution is Li implies the Wronskian is non-zero at a particular point, right? So instead of
Sir, can you repeat this part?
no, you can go through the video again later, right? Because I want to cover the next part. So if you have doubt, you can ask me after the lecture. So in the converse part, what we need to show? We need to show that Wronskian is 0 at particular point. So instead of proving Li implies Wronskian is non-zero, we will prove Wronskian is 0 implies the solution is not Li. So solution is not Li means it is LD, right? Linearly dependent. So let us discuss the converse part. First, we are assuming that the Wronskian is non-zero at particular point or fails. So that means it is 0 everywhere. Right. Conversely, suppose that Wronskian is 0 at each point x in the interval. Right. So if it is 0 at each point, what is our goal? Our goal is we want to prove the solution is solution y1 comma y2 is linearly dependent. So that is we want to show. So once again here also, whether we are showing Li or Ld, we will always start with the linear combination. So let C1y1 plus C2y2 is equals to 0 is a linear combination. So we are starting with this condition. And if we want to show it is LD, that means we need to show that one of the C1 or C2 is non-zero. Right? So from this condition, what we'll get? So therefore we get the linear equations. So first equation is C1 by 1, and since we are differentiating this equation, this is the same equation along with its differentiation. Differentiation is y1 dash x plus y2 dash x is equals to 0. Right, so we got this system of linear equation by this particular equation. And now once again we want to check that does this system of linear equation has a non-trivial solution. Non-trivial means both the C1 and C2 is non-zero. So that is possible because of this condition. So what does this condition means? This condition means Wronskian is 0 at every point. So let us call this equation B. So since Wronskian is 0 at every point x, we get y1x into y2 dash x minus y2x y1 dash x to be 0. So this is a system of linear equation in C1 and C2. We need to identify C1 and C2. We need to find out that. And y1 and y2, y1 dash, y2 dash are fixed if we fix x, right? And for that particular x, we have this determinant is 0. So what we are getting is we have a homogeneous system, and coefficient of homogeneous system, the determinant of that is 0. So we know that such a system has infinite solution. Right? The system of linear equation in two variable, if the coefficient determinant of that system is 0, if the coefficient determinant is not 0, then it is a unique solution. But if it is 0, that means it is a infinite solution. So since this is 0, we get this, and hence the system B has infinite solution. So since it has infinite solution, we get a solution such that we can get at least one solution such that either C1 is not 0 or C2 is not 0. Right, so that means we get a non-trivial solution of this system. And what it gives is, if we get C1 is non-zero or C2 is not 0, then from this condition we get y1 and y2 are LD. Right, so therefore y1 and y2 are linearly dependent solutions of the given ODE. Second order homogeneous linear differential equation. So let us go through this statement once again. So whenever in the example we want to check the two given solution y1 and y2 of the homogeneous second order differential equation are linearly independent, only thing we need to check is the Wronskian is non-zero at a particular point. So we don't need to check Wronskian is non-zero at every point. The only thing we need to check is Wronskian is non-zero at a particular point. So this is the method to check whether two solutions, whatever we will get, is Li or Ld. But on the other hand, first thing is how to find the solution, right? If we get the solution, we can check using this method whether the solution is Li or Ld. Yeah, so in general, finding such a solution is not easy because we are working with second order differential equation. Even in the first order, we have seen that every time we may not get the solution. So sometimes we discuss only existence and uniqueness without finding the solution. So let us discuss one method that whenever we have a homogeneous second order linear differential equation with constant coefficients. So such a system, how to find the solution, right? So what do we mean by constant coefficient? Constant coefficient means the coefficient of y double dash, y dash and y is a number, right? So consider such a equation. So consider the differential equation a times y double dash plus by dash plus cy is equals to 0, where x is in some interval and a, b and c are constants or numbers. So in such a case, how to find solution? So we usually write such a differential equation in the form. Yeah, so we can rewrite this as a times second derivative of y plus b times first derivative of y plus c times y is equals to 0. Right. So this is same as a times d square y by dx square plus b times dy by dx plus cy is equals to 0. So this form means it is of the form L of y is 0, where L is this differential operator. So operator means it is a linear function. Right. So we consider L to be this bracket thing, then this equation, given equation, is nothing but Ly is equals to 0. And note that L is linear. L is linear function, linear map. So it is the same thing that if y1 and y2 are solution, that L of y1 plus y2 is L of y1 plus L of y2, right? So that way you can easily check that L is the linear operator. And in other notation, we simply write L as, so instead of writing d square by dx square, we will write as d operator. So d represent kind of d by dx, right? And d square represent d square by dx square. So whenever we will have this operator, either we'll use this notation or this notation for L.
Sir, वो क्या लिखा सर? L is linear.
Yeah, so that thing I mentioned that if y1 and y2 are solution of this equation, so that means Ly1 is 0 and Ly2 is 0, right? Using we have observed earlier that if y1 and y2 are solution of this equation, homogeneous equation, then y1 plus y2 is also solution of the homogeneous equation, right? Because a y1 plus y2 double dash plus b y1 plus y2 dash plus c y1 plus y2 is equals to basically Ly1 plus Ly2, and y1 and y2 are solution of this, that means Ly1 Ly2 is 0, right? So the important thing is here is that the equation should be homogeneous. If this is not homogeneous, then it is not a subspace of continuous functions, right? So right hand side must be 0, then only we can say this. Yeah, L will be always linear operator. So that is what we use here without equating to 0. More or less, this computation says that L is linear. Right? The left hand side is essentially L of y1 plus y2. Right? Okay. So essentially here we are using that derivative is a linear function.
सर आपने वो लिखा है ना सर, नोट दैट L is linear. फिर क्या आगे क्या लिखा है? मैप लिखा है.
In the other notation, linear map, yes. Note that L is a linear function.
Okay.
So in other notation, we will use L to be this one, right? So further note that whenever we apply, yeah. So now the question is, what is the solution of this differential equation? So whenever we will find solutions, we will always assume that certain function is a solution, general function, and then we'll find coefficient of or unknown of that solution. So usually we have observed that in differential equation, in some of the equation, the solution is of the form yx equal to e power x, right? So let us try whether such equation can have solution of the form e power x. So if we apply this operator on, so assume that yx is equals to e power mx is a solution of the given equation. Right. So if it is a solution, that means it must satisfy the given equation. That means L of e power mx is 0. And what is L of e power mx? That is a times second derivative of b times first derivative plus c times the function y, that is e power mx. So now if we apply this operator on e power mx, we know that first derivative of e power mx is m, and second derivative of e power mx is m square. So that means we get a polynomial am square plus bm plus c, right? And from the equation we know that L of e power mx is 0, right? So this condition gives us whenever am square plus bm plus c e power mx is 0, we know that e power mx can never be 0. So that means we get the polynomial em square plus bm plus c is equals to 0, right? And so by assuming e power mx is 0, what are the possibility of m? Possibility of m is m must satisfy this equation, am square plus bm plus c is equals to 0. Yeah, so let me stop here today lecture.